Okay, so far what we have done is that we covered basics of group structure, the algebraic structure, subgroups, etc. and cycles, cosets, and then the SN group and Kelly's theorem, important theorems, normal subgroup. So all this we have done for a group at a general level. What we are going to do next is to study representations, because those are the things that are actually used. So far we can say that effectively abstract so properties of abstract type applicable to all groups. So now we begin next with the idea of representations. And just to remind you, we have divided this course into two roughly equal halves of discrete groups and continuous groups. So far we are doing discrete groups. So although a lot of the general things said about groups will carry over for the continuous groups, but there are some essential differences. So we did the generalities, and then we are going to do representations. And the next part after the mid-sem approximately will be continuous groups. Where again we will need generalities. So I will say more general, I shouldn't say more generalities, but generalities special to them. So these very basic properties will mostly apply except for a few exceptions, but there is the structure of the group as a continuous groups leads to some very interesting properties, and again representations, but more through some physics examples. Here also in discrete group representations there are physical examples, but it is difficult to actually cover any of them very seriously except for molecular vibrations. So we will take molecular vibrations, but the applications to lattice groups is rather involved. So you really have to delve into some condensed matter systems to really see their applications. Okay, so let us begin with this idea of representations. And by this we mostly mean matrix representations. And what that means in turn is, in the terminology we have defined earlier, the realization of the group through linear algebra. with vector spaces as carrier spaces. So the permutation groups were very powerful overarching groups for discrete groups, but that doesn't carry over to the continuous groups. Whereas this particular matrix representation idea carries over to continuous groups more or less without with only the special things being different, carries over to continuous groups case. Again with some changes due to continuity conditions. Okay. But the use of the cycle representation etc. is going to go because we no longer have SN groups in the case of continuous groups. Okay, so what is it about matrix representations? One is whenever we have a geometric quantity, we have a geometric system or a geometric symmetry, we can always represent rotations as matrices. This is well known. So where we have things like rotations and reflections, we use the rotation matrices. So this is the simplest way of and we will see that all the discrete groups can be described in this way as linear algebra operations, but when it is geometric it is the most obvious. So the as a first example, and since I have these slides from this, I will put up these slides. K. Horn, all his affiliation is there. So here is the set of matrices. Remember the triangle, you can an equilateral triangle, you can rotate it and you can also flip it along the its altitudes. You can represent this as matrices, as 3D matrices. So suppose you put it in the xy plane, put the triangle in xy plane, all the operations you now do are not going to affect the z axis. Okay. So in this 3×3 representation of rotation matrices, the lowest corner is always 1 and the lowest row and the last column are just 0, 0, 1. Okay. So in all the 6 operations written out, it is like this, and this transparency of course goes into some detail of how this has to be got, but the point is that we have firstly of course the identity element which will be represented as identity matrix. So you can either make a geometric association, I think in this case just think of geometric association. So if you do not rotate the triangle at all, then you should represent it by identity matrix. Then we have rotations by 120 degrees and 240 degrees, for which I in a hurry dropped the minus signs last time, but this is the rotation matrix for 2π/3 and 4π/3. So you can see there is -12, -12, and the whenever there is a real rotation, there is a sine theta and minus sine theta. It's always antisymmetric in terms of these signs. And so clearly this it is in whatever second quadrant, then it is in third quadrant, so you get this minus sign. So this, the top three represent just the usual rotations, and it constitutes group C3, the cyclic group of order 3. Then of course there are three possible reflections, and the way they are captured are here. So you can think of this as, so this flips the x-axis basically without touching the y-axis. So this is when the triangle is coming back here. So we have x and y and z is coming out. If I do not touch the, so if I flip about this axis, then basically x goes to minus x. So this one matrix would just send x to minus x, but then there are two other matrices which are flips about this and the other two altitudes. So one is this, and then flip about this, and then flip about this. So these become, and let us try to identify by going back and forth a little bit. So you can see that sigma v prime is the x-axis flip. Now let us try to identify what this does. It is, one way to think about it is, you compare it with say one of these are the proper rotations. So if we compare this and this, then basically the top row is, its signs are changed, whereas the bottom row signs are not changed. Okay. Of course, if you will compare with this, then you will find that the first row, first column signs are changed, and second column signs are not changed. But let us think in terms of the row. So this is called sigma v double prime, and where this sign changes. So can you think of what sigma v double prime is in our diagram? Yeah, so this is sigma v, and let me write down the sigma v double prime matrix, which is half and minus half and minus square root 3 by 2 and square root 3 by 2, 0, 0, 1, 0 and 0. So which is sigma v double prime? So yeah, I was going to do. So one thing is to put here a labeling for convenience, call this A, B and C. So A, B being exchanged is this. Then if you exchange C and A, is that what is sigma v double prime? One thing is to let it act on 1, 0, 0. So suppose on, so if I have a vector in this direction, let us see where it goes under this operation. So acting on so what does it do? It sends 1 to plus half, right? This row into this column will produce a half, and then this row into this column will produce plus square root 3 by 2 and 0. So it will send it into this direction. That doesn't tell us. So we have to study both x and y. And if we take y, this is taken to So a generic vector here, the x coordinates remain within the first quadrant, but for the y coordinate it goes into this quadrant. So that is, yeah, so we are trying to decide which flip it is, which of the flips. It is not a rotation matrix, but it is a flip, it's an improper rotation. Right, it's not orthogonal, but it is a transformation of the 3 points A, B, C into themselves. And we are trying to identify which it is. It is a, so we note that the matrix -1, 1, 1 is also not orthogonal. It is orthogonal, but determinant is not equal to 1. So this kind of a transformation will be a rotation plus a flip combined with, it's an improper rotation. Okay, let us see. So sigma v double prime has half and minus, this minus 2/3. Right. That there is a minus 2/3 there. So in this writing there is a minus sign here. This acting on this produces this and minus, and acting on this it produces, so this is correct. So in other words, the question is, what is the eigenvector of this, which is the vector this matrix does not flip, it does not change. And so try to figure out whether this is sigma v double prime or this. It's probably shown in this, but I just thought that we would think about it before going to it. So basically those are the operations. Yeah, so is that now okay with this minus sign? So this is what we are saying. Right, I understand that you are saying this was not orthogonal, but with this sign it will be orthogonal, but the determinant is not -1. So coming back to this, basically the top row contains the proper rotations, and then the bottom row contains one key reflection which is a -1, and actually the other two you will get out of these proper rotations by just a multiplication of this to them. Okay, so that is one way of thinking. So this minus sign multiplying, yeah, so first we perform the rotation, and then if we multiply by this, we will change the signs of the top row, that will give us this. So I claim that, oh, and let us decide which is this rotation, because this rotation has a positive y, the y component remains positive, right? If I have 1, 0, let's say 45-degree vector, it will make the x coordinate negative, but it will leave the y coordinate positive, so it is still in the second quadrant. So it is a rotation by 120, and this is a rotation by 240. So if we perform a 120 rotation and then make the x-axis flip, what do we expect? So you take this to this and then make flip about the x-axis. That will have first and A, C on next page. So if we rotate this, we send B over here, we send A over here, oh God, A, B, C, yeah, so B goes there, A goes there, and C goes there, and then I do an x go to minus x flip. It will put this B here, A here, and C here, right? So the net effect is to leave A unchanged. A remained where it is, and it flipped B and C. So this operation is sigma V double prime, because we did a sequence of, so we have identified some element like this, okay, and what we have just checked is that this is equal to, so we are reading from right to left. So if we first do minus a half square root 3 by 2 minus square root 3 by 2, a proper rotation. So our claim is that this matrix with the top row signs reversed can be got by taking the proper rotation, which is this. This is the first step. This corresponds to this step, rotation by 120 degrees counterclockwise. And then we followed up by x go to minus x. We can now look at the configuration and compare with the original. We see that the vertex A has not changed, whereas B and C have been flipped. So that is what is sigma V double prime. So this is equal to so in this way we can represent, oh this one, thank you, clockwise. Okay, so you figure it out if I have done it wrong. I thought that it was going counterclockwise. Okay, then of course this will get exchanged with this. So I will not spend more time on this here, because as I said, there is input-output problem. To look at it here, draw it here, think about it and tell you is not all easy for me. All I do is take a simple known vector, no, on a, so my argument simply was looking at the signs here. If I put a vector here 1 1, okay, which is pointing in 45 degrees direction, and apply this, it makes the first component, or it leaves first component positive, you are right, because it is square root 3 by 2 minus a half, and this is bigger, and then second row and that will make it definitely minus. So it puts it in the lower quadrant, in the fourth quadrant. So you are right. So it is actually then it is the other one. Okay, good. So we actually did find out. So this one, this is not the one. This is a rotation in the counterclockwise direction, which is the way we usually write. The matrix C31 written there is not that one. So this happens with C32 actually is going to produce this. Yes. Yeah. So I wrote here C32, that is C32 as given here is going to do this and this, and that is what produces sigma V double prime. But I think our characterization of sigma V double prime is correct, because so this is correct, that it leaves this sequence is correct. Okay, our calculation here is correct, that we can write this matrix, which however is, here it is C31. So that is the only problem. This is called C31. If we do C32, then we get sigma V double prime, which is flipping C and B. If we start with C31, it should give you sigma V triple prime. And for this, the corresponding pictures, I don't want to draw too many. ABC was turned like this, now it has to go like this, and then flipped x to minus x, so you will then get sigma V triple prime. Similarly. Okay, so by taking care of the directions of rotations and the flip, we can get all the matrices. Now, in terms of matrices, we get all the matrices are orthogonal. However, the lower three do not have determinant equal to +1. They have negative determinant. Okay, these form the usual rotations. Now, we come back to the idea of representations. The point is that as far as these matrices are concerned, this one which was below goes for a ride. Okay. Nothing is happening to it, it is representing the z axis. So actually from the point of view of representation, we say that this is a reducible representation. It has, so this 1 1 1 is also a representation of the rotation group of this threefold rotations, but the trivial representation, where every element is represented by the same element 1. You know, 1 is always a realization of any group, because 1 multiplied by itself any number of times gives itself. So it's a many 1 map. It is an unfaithful representation, but a valid one.